Alright, hey guys, we are going to go through some topics and statistics. The purpose of this video is to help you better understand some of the things that you've read about, that we've learned about, that we've talked about, and in general, just to give you a basic, a more in-depth background to some of the things that we've been discussing and the things that you will see and probably have seen in your articles. Okay, so first I'm going to start by going through a few different statistical tests that you may see within articles. And essentially the purpose of this is that I want you to have an idea in the back of your mind when you're reading these articles and you see somewhere in the method section that they used a one-way ANOVA. You have at least a general idea of why they use that particular test. Now, you may not fully understand all of the calculations or in detail everything about all of these, but it is good to have an understanding of the different tests that are available to use and why they exist. So the first one that we're going to look at is called the kappa. Now this particular statistical test is generally used when we're looking to evaluate a measurement. So pretty much everything I shouldn't say pretty much. Everything should go through research. This is the reason why we're focusing on evidence-based practice. That includes measurement or tools that we use to measure. So when you're using a FIM or you're looking at a pain scale, those things need to be determined if they're valid and reliable. Now, when you use different measurements or assessments like a FIM, I'll just stick with that. Often you may have one rater who may do it multiple times for the same patient, or you may have multiple raters that do it for the same patient, for one patient. Well, in order to understand how valid and reliable a FIM is, you want to do some background research and some type of statistical test to determine raters' agreements. So the kappa is used for that. So when you're reading literature on interpretation of diagnostic tests, you generally focus on sensitivity, specificity, and predictive values and likelihood ratios. Essentially, these address validity of the test. Okay, now that's probably a little more than what we'll focus on, but again, this is some background. So, but if the people who actually interpret the test cannot agree on the interpretation, then the test is of little use. So essentially, if multiple raters are getting a different interpretation for a particular measurement, such as, or like the FIM, then that FIM serves no purpose to us in our field. So therefore, the kappa statistic, K, which is is represented by a lowercase k, is a chance-corrected measurement agreement. It is used to measure two or more independent observers that are evaluating the same thing. And it is used to examine relationships between three or more nominal level variables. So we're looking at agreements and we're calculating agreements. So an example of that would be, suppose two clinicians want to establish their inter-rater reliability for evaluating level of function for self-care on a 3-point scale. The data can be summarized to show agreements by arranging them into a calculation. The kappa is then used to measure those agreements to determine an answer. So that's just a little bit of background, but that's the kappa. Okay. Another one that we often use is the Mann-Whitney U. This is a test that is used to compare differences between two independent groups when the dependent variable is continuous. Okay. This is as you see, it is in bold. This is a non-parametric test for differences between two groups that use ordinal level data. Now, if you remember what ordinal level data is, it's ranked data. This is why we use ranks within Mann-Whitney U's. So here's an example. A researcher is interested in the effect of a body position of a person's ability to relax. And we're studying or we're looking at two different groups that are put into a pre-test and post-test design. So you have one group sitting in the other position supreme. Now, that's just a question. Here's some data that I just put together. Look at this data. So you have your two groups. Here's, oh, I'm sorry. Here's group 1. Here's group 2. Here's the data for group 1. And here's the data for group 2. Now what I've done is I took this data as a whole and I ranked it. So 1, 2, 3, 4 for the 15, 5 for the 20. So essentially I'm ranking it from 0 all the way up to whatever the highest number is within this data. And let's see what the highest, I think it's 50. So 11 should be the highest ranked number. Then we went and did a total for each rank down here. Okay. Now, this is the data. So the purpose of this is to determine if the differences between the sums of the ranks is sufficiently large enough to be considered significant, because technically any differences between the ranks should be the result of chance. So we're using this test to determine if there is a difference between the sums of ranks. Here are the ranks. Here's the sums of the ranks, okay? Now again, this is a non-parametric test for the differences between two groups that uses ordinal level data, okay? All right, let's take a look. Let's take a look. All right, so the next one that we're going to talk about is multiple regression. This is an extension of linear regression, and it's used when you want to predict the value of a variable based on the value of two or more other variables. Now, again, I'm going to bold out so you understand. It's used to determine if a ratio level variable can be predicted by two or more variables. This is my example. Can income be predicted by education level and marital status, your two or more variables? This is a ratio level variable, and it's looking to be predicted by two or more variables. Now, please note the difference between linear regression predicts one variable, while multiple regression predicts two or more. And remember, regression, relationship, correlation. Let's take another look, or not another, but let's take a look at the next one. The ICC, okay? This assesses the reliability of rating by comparing the variability of different ratings of the same subject to the total variation across all ratings of the subjects. This is used for testing measures, okay? Similar to CAPA. Okay, it does not require the same number of raters for each subject, and that's why this is a great one, because there's a lot of flexibility. But the point to note is that this intra-class correlation ICC is used to measure reliability for repeated measures or association between three or more variables. Let's take a look at the next test. Okay. Now for this one, we're looking at three or more groups, and you want to understand the difference between those groups. So if a collection of data samples are independent, if they come from unrelated populations and the samples do not affect each other, by using the KW, you can decide whether the population distributions are identical without assuming them to follow normal distribution. Okay? So, example is that if you wanted to study the effect of three modalities for relieving chronic lower back pain, and let's say you randomly assign 17 subjects, capital N, for your total population is 17, to receive, 6 of them receive ice, 6 of them receive a hot pack, and then 5 of them receive an ultrasound. Okay, the scores are then recorded as the change in level of pain from pre-treatment to post-treatment levels. And that's when you would use this test. Now, again, the thing to note about this particular statistical test is that it's a non-parametric test to examine differences between three or more groups. Alright, now let's look at the independent t-test, which you probably will see fairly often. This is a parametric test for differences between two groups. It is used when the means of two independent groups of subjects are compared. Groups are considered independent because each is composed of an independent set of objects with no inherent relationship derived from repeated measures or matching. For a t-test, if you have three or more groups, you do not necessarily need to run a multiple t-test, and please note there are a few different t-tests out there, but I just wanted to note that. So two things: it is a parametric test for differences between two groups, okay? And just side note or to note, for a t-test, if you have three or more groups, you don't always necessarily need to run a multiple t-test. And that's all I'll say on that one for now. Now, paired t-test, okay? This one is when you're looking at, is there a within group difference across two time points? Okay. Often researchers use repeated measures or matched designs to improve the degree of control over variables in a study. In these subjects may be matched on relevant variables such as age or any other variable that is potentially correlated with a dependent variable. Okay. In these types of studies, data are considered paired or correlated because each measurement has a matched value for each subject. So the paired t-test can distinguish if the values are significantly different from each other. It essentially analyzes different scores within each pair. So it looks at, is there a within group difference across two time points? Pearson product moment correlation. This is also known as the Pearson correlation coefficient. This is used to determine a relationship between two ratio level variables. Okay, is denoted by a lowercase r, and it indicates how far away all data points are to the best fit line. So now let's take a look at this. You can have different types of correlation. You can have positive. As you notice, they're kind of all going upwards and they're all going in the same direction, and they're pretty much bunched together. Negative. They go downward and all kind of bunched but going the same way close together. Or you can have no correlation. They're just scattered with no direction. Okay. When you're looking at the Pearson correlation coefficient, you're looking for that best fit line. And these are examples of different best fit lines. So no correlation, negative, negative, positive, positive. Close enough to positive. It's kind of scattered. Okay, the next test, logistic regression. This one has a little more information. Okay, so often questions of prediction involve outcomes that are categorical. Nominal data. Example, why some individuals experience recurrent falls. In logistic regression, or I'll just say LR, the dependent variable only has two values. That is occurrence or non-occurrence of an event, or presence or absence of a condition, okay? The outcomes is measured with the dichotomous variable, and the dependent variable is what you want to predict. It must be dichotomous and should only contain data coded as 0 or 1. This is your nominal data, or also known as categorical. You're looking at what is the probability of an event happening based on the value of a known factor when the dependent variable is nominal level data. Okay, and just so that you understand, correlation is based on a scale of 0 to 1. The closer you are to 1, the stronger the correlation or the association. So if you have a correlation of 0, this is weaker or negative or non. if you have a correlation of 0.80, you have a positive, strong correlation because, as you know, or as we said, it is closer to 1. Now, this is a little side note about correlation, but important, and it will be asked within the quiz. But specifically for LR, you're trying to understand what is the probability of an event happening based on the value of a known factor when the dependent variable is nominal level data. ANOVA. This is another one you will see fairly often. This is a parametric test used to examine differences. I'll fix that. Okay. Fixed. So this is a parametric test used to examine differences between 3 or more groups. Generally within an ANOVA, you will see a F statistic. This is what you will find when you're looking at different charts. Okay, there are many ANOVAs. It can be a one-way or it can be more. So essentially, you are using. I just wanted to note that if you see an ANOVA, you may there are many types of ANOVA. So don't freak out if you see like a one-way or if it says multiple or whatever the case may be. There are many ANOVAs that you can use, and essentially, you use this to compare the means of more than 2 samples. Okay. Now here's an example. Suppose we want to test the effect of 5 different exercises. For this, we recruit 20 men, assign one type of exercise to 4 men, making 5 groups total. Their weights are recorded after a few weeks. We may find out whether the effect of these exercises on them is significantly different or not, and this may be done by comparing the weights of the 5 groups of 4 men each. Now, to do that, you would use an ANOVA to compare the means of more than 2 samples. Okay? Chi-squared. Now, this is used to examine differences between 2 groups of nominal level data. Categorical data may be displayed in contingency tables, and the chi-square statistic compares the observed count in each table cell to count which would be expected on the assumption of no assumption between the row and column classifications. It can be used to test the hypothesis of no association between 2 or more groups, populations, or criteria. This is an example of a contingency table, and this is a generic example, and I'm looking at, is disease associated with exposure? So essentially, you would have your columns yes or no on each side, because remember, it's a contingency table, often 2 by 2, and you are just recording that information. Now remember, this is nominal level data. Okay. The z-test we've talked about, or you should have read about at this point, and the purpose of the z-test is to look at a group to a population, and you're looking at whether there's normal distribution, as large samples should be as normally distributed as possible, and this is just again an example of what we're looking at when we're looking at a z-test. But I won't go into detail because we've talked about this. Hypothesis. So we always have a hypothesis within our research, and often you will hear null and alternative hypothesis. Well, what does that mean? So when you see HO, this is the null hypothesis, and that essentially means there is no difference. When you see a HA, this is alternative, and that means there is a difference. Now, when you have a null hypothesis, this is essentially saying the assumption that nothing will change, and the more you increase the number of hypotheses tested, you increase your chance for a false positive. Okay? Again, the assumption that essentially null hypothesis means, or is the assumption that nothing will change. And it's important to understand that the more you increase your number of hypotheses tested, you also increase your chance for a false positive. And now that I'm looking at that, I'm going to separate that so that you understand that separately. Okay, so a null hypothesis, again, is the assumption that nothing will change. The more you increase the number of hypotheses tested, you also increase your chance for a false positive. And I'll go and explain what a false positive is. So, when you reject HO, or you reject HO, or you're null, if the p-value is less than or equal to 0.05, meaning it is statistically significant. You do not reject it if the p-value is greater than 0.05, because that essentially means it's not statistically significant. So let's look at two examples. If alpha is set to 0.05 and you computed a p-value that is 0.30, then you should not reject the HO because the p-value is greater than 0.05. Now let's look at an opposite example. If alpha is set to 0.05 and you computed a p-value that is 0.001, then you should reject the null hypothesis because it is less than or equal to 0.5. So essentially you're saying this is statistically significant, this is not, depending on whatever you're looking at. Now, we talk about alpha. As you can see, it's alpha when we're talking about within hypothesis, within your hypothesis. But what is alpha? Alpha is level of significance. P-values are measured against this value. So the value of alpha is associated to the confidence level of our test. And I kind of give you an example. So this is, remember this is an arbitrary number. So when you see 90%, that's essentially, or essentially that's 1 minus 0.90, so 10. When you see 0.10, that's how you get that alpha is equal to, or alpha is less than or equal to 0.10, or alpha is equal to or less than 0.05 or 0.01. That's based on these level of confidence, 90%, 95, and 99. Now, in general, for results with a confidence level of, or CI or CL, or confidence interval, the value of alpha is 1 minus C divided 100. But generally, you just know when you see this 95%, that's where that 0.05 is coming from. That's essentially 95% confidence interval. Okay. Now, the point of alpha is it's the maximum probability of committing a false positive. Okay. Now, p-value is the first step. The first step is to state your null hypothesis. That really the disease does not affect the outcome you are measuring, so all differences are due to random sampling, and that's just an example I'm using. And it looks at, the p-value looks at a statistical significance based on the alpha presented. It is it statistically different or statistically significant or not statistically different or not statistically significant? P-values simply provide a cutoff beyond which we assert that the finds are quote-unquote statistically significant. By that convention, that is, the P is less than 0.05. And p-values represent the probability that a result was due to chance. Confidence intervals are used to describe the amount of uncertainty associated with a sample estimate of a population or sampling method. Now, we talked about confidence intervals a little bit when we talked about the alpha value, alpha and the p-value. So you should have an idea now. That 90% confidence level, essentially, if it could be 90 or 95, but essentially it's what we sorry, it means that we would expect 90% of the interval estimates to include the population perimeter. So somewhere in that 90% or 95% or so on lies our true answer. Okay. Now the biggest effect on confidence intervals is the number of incidents or number of occurrences. So that's important to note. For confidence intervals, the biggest effect on confidence intervals is the number of incidents or occurrences. Now we've talked about continuous data. So what is continuous data and what are some examples? You have continuous data and you have discrete data and dichotomous data, but here we're going to essentially look at continuous data versus discrete data. Continuous data can take any value within a range and measure it. It's a measurement and it can use decimals. Examples of continuous data is quality of life. For discrete data, it can only take certain values and it's counted and is used as whole numbers. So, an example of discrete data would be well, there are many. I'll just say the number of pregnancies that a woman has had because, well, you can't have a decimal. So, a woman could have had one child or two child, meaning they had one pregnancy or two pregnancy. And that's just an example. I know there are other cases, but that's an example of discrete data. Now, I just want to talk a little bit more about understanding dependable variables because I've talked about independent variables and dependent variables. So, I'm going to use an example of what I'm trying to explain about dependable variables. So, I give you the example, or I'm giving you the example. You conduct a physical activity intervention for children in an effort to improve attention in the classroom. One group receives the intervention and the other group receives no intervention. You calculate a t-test to see if the groups have different levels of classroom focus. What is the dependent variable? Well, if you're looking at, and I'm sorry, I should have said attention. I should have said attention here. But if you're looking to improve attention, then you would assume that attention is your dependent variable because your results are dependent on their ability to pay attention. That's essentially what I wanted you to understand. This is just an example. I'm going to talk a little bit about type 1 and type 2 error. These are actual definitions and then I'll put it in plain tense for you. So type 1 error is rejection of the HO when no true difference exists. It's due to chance because you don't know if you made it, but you can make it very unlikely. It's the rate of it happening, alpha set by investigator, which is what you usually see, the 5% or 95% confidence interval or 0.05 for your p-values. Type 2 error is failure to reject HO or your null when a true difference exists. This is due to chance or small sample size. It can be estimated based on group size. Now, what does that mean, right? These are textbook definitions, but let's look at it in plain sense. Alright, so essentially type 1 error is a false positive. Now, previously I told you I was going to get to that false positive, and here it is. That type 1 error is a false positive. So when a clinician falsely detects the presence of a disease or condition when in reality no disease exists. So example, falsely diagnosing breast cancer through mammogram screening when in reality breast cancer is not present. That's an example of a false positive. That's a type 1 error. Type 2 error is a false negative when a clinician falsely concludes that based on the test results, no disease is present when in reality a disease does exist. Now, sorry. Last but not least, I want to talk about the differences between the types of statistics that exist. Now, through this lecture, I have mentioned that some of them are parametric and some of them are non-parametric, but what does that mean? So essentially, I want you to take a basic understanding of it at this point. And the basic distinction for parametric versus non-parametric is if your measurement scale is nominal or ordinal, then you use non-parametric statistics. If you are using interval or ratios, then you use parametric statistics. Interval or ratio for parametric, and nominal or ordinal for non-parametric. So it just depends on the type of um, data and the measurements that you're using for your data collection. Now, this was just a quick overview, but hopefully this was a little more helpful in kind of defining some of the things that we've looked at and that we've talked about and that you've read. Now, as always, if you have any questions, please do not hesitate to ask. But this is it for the Module 2, Week 2 stats lesson.